Okay, so welcome to today's seminar. Today we have with us Chiara Stuardi. Chiara did her master thesis in physics in Torino, and then move on to carry out her PhD in astrophysics in the University of Bologna, where she is also now doing her first postdoc. Chiara focuses on the research of magnetic fields in galaxy clusters and the cosmic web, where she carries out observations performed with different radio telescopes and use simulations in order to study magnetic fields, the evolution and the amplification of the fields during larger scale structure formation processes. And today she's gonna talk about radio relics in galaxy clusters. So please start. Take it away.
Yeah. Thank you for the nice introduction, and thank you to Carolina and Valentina for inviting me to give this talk today. So let's start from the big picture. So basically, why do we care of galaxy cluster, their magnetic fields, and magnetic fields in general on the larger scale of our universe? That is because our universe is magnetized. This is a large-scale simulation of a galaxy of our universe. This is a box. This is the size of 30 megaparsec. This is an inset, and here we can see the gas column density, the temperature, and the magnetic field. So the universe is structured with like a web with the nodes that are of course galaxy cluster, and we know that all this large volume is permeated with a very weak magnetic field. We don't know yet the origin of this magnetic field. It can be primordial, meaning that it develops in the first stages of the evolution of our universe, or it can be also astrophysical, meaning injected by different sources, mainly AGN and radio galaxies, into the external medium. But what we know is that, in general, a very weak magnetic field can be amplified by the structure formation processes so that it can reach the micro-Gauss level in galaxy clusters, so in the nodes of the cosmic web. And here, in cluster where the density is higher, we can start to study magnetic fields via their synchronous emission, radio emission, or polarization, so rotation measure properties. And so let's go into the detail of what we see in a galaxy cluster. This is a overlay between optical, X-ray, and radio emission of a galaxy cluster. And I will go into detail of all of these images. So in the background, we have the optical galaxies, of course. And although galaxy clusters are named by the galaxy, instead galaxies constitute just the 5% of the mass of clusters, while the 80% is in the form of dark matter. And we can see this mass thanks to gravitational lensing study. And here we see the contours of the gravitational lensing. In blue at the center, we see instead the emission, the X-ray emission via thermal Bremsstrahlung of the plasma. That constitutes the 15% of the mass of cluster and is called intracluster medium. In red, instead, on the right, we see radio emission from this cluster that is both connected to single radio galaxies, like in this case, what we know as they are IGN, but is also more diffuse on larger scale in this cluster, in these two features. And in this case, in this cluster, what we see is the presence of a radio relic in the outskirts and of a radio halo. And the fact that we see synchronous emission on this large scale tell us that galaxy clusters are filled with magnetic fields and cosmic rays, in particular cosmic ray electrons. And this is the non-thermal component of galaxy cluster that in number can be subdominant, can seems to be subdominant, because the cosmic ray number density is estimated to be about 10 to the minus 10 per cube centimeter, while we know that the thermal gas density is 7 order of magnitude higher, while the cosmic ray energy density is just 1% of the thermal one. The magnetic field is very weak, as I said, between 10 and 0.1 microgauss. So why do we care if this is a really subdominant component in terms of energetic? Well, this is because it has important effects on the physics of galaxy cluster, because magnetic fields can affect, for example, the heating conduction. They are linked to the plasma, to the thermal plasma, so they are strictly connected to all the acceleration of particles that happens in the plasma. And so it can be, so magnetic fields are important to understand also cosmic ray acceleration models. And of course, as I said, the value of magnetic fields in cluster is important to understand the magnetogenesis, so the origin of magnetic fields, and also to understand effect of magnetohydrodynamic in high beta plasma. So it's very important to understand which is the origin of these large-scale radio structures, and to study the connection to the magnetic field. Going a bit more in the detail of the sources that we are seeing here, on the left, we see a radio helix, as I said, while on the center of the cluster, we see the skull radio halo. And these two sources are both megaparsec in size, so they are large, almost how much as the galaxy cluster, and both are found in merging galaxy cluster. So in cluster that has just undergone a major merger event. But radio helix are shaped and are generally found in the outskirts of galaxy cluster, and they are strongly polarized, reaching 20–50% polarization at 1.4 gigahertz. While radio halos are generally roundish, found in the central region of galaxy clusters, and are not or weakly polarized. There are some detection of polarization from halos, but most of them are debated or due to some filaments in the radio halo. But as I said, they share the common feature that are megaparsec in size. And this drives a problem, let's say, that is the fact that the diffusion time in galaxy cluster of the particle in galaxy cluster is much larger than their radiative time. So that means that particle cannot reach such large distances without being continuously injected and accelerated. So that means that we need to have some in situ particle acceleration processes that can explain this large-scale diffuse emission. And from the beginning, when these sources were firstly discovered, it was clear that there was a connection between this cold diffusion problem and the fact that both of these sources are present in merging galaxy clusters. So there is a connection between the merger event and the presence of such sources. In fact, we know that when galaxy clusters merge, a lot of energy is injected in the cluster. These are the most energetic events in our universe, and so this energy is dissipated in form of shocks and turbulence that are injected in the intracluster medium. And both of these can accelerate particles and also amplify magnetic field, leading so to the synchrotron emission on the large scale. And both turbulence and shocks are both observed and theoretically expected in cluster. In particular, we observe shocks in the outskirts of galaxy cluster, and we can observe them through X-ray observation and also measure their Mach number that is generally between 3 and 5. And generally, we observe shock at the same position of radio helix. So there is a strong connection between the presence of shock and helix. So coming back to our example cluster, what we think is that turbulence is able to accelerate particle on the central region of galaxy cluster with also the thermal electron density is higher, while shock are able to accelerate particle in the outskirts, forming radio helix. Now I will show a movie created for in an image contest. So it's bit astonishing, but it comes from real simulation and real observation, and I will comment it step by step. So this was an image content made for the Very Large Array Observatory. So here you see different baryonic gas density clumps, mainly subcluster, that are merging together, and you can see them from the color from red to yellow. Then there is in blue the synchrotron emission of particles that are accelerated in this merging process by shocks. And in white, you see these Lagrangian tracer that basically are a group of electrons that are accelerated by the shocks. So this is an artistic view, but as I said, is based on real simulation. So while the merging process proceeds, particles are accelerated many times by shocks. And at the end, what we see is cluster scale radio emission that we, of course, see in projection. And with our simulation, we are able to reproduce real observation that we have of diffuse emission and galaxy cluster. This is an example of a double radio relic system where two relics are observed in the opposite side of the cluster. This is the first relic. And then we will go to the other one, this one. But we have also a system where we see just one relic, and we have a highly resolved observation of the system. And you can see from this image, for example, that the systems are not just arc-shaped, but they are strongly filamentary, they have substructures, and they are very complex inside. Okay, so this is the end of the video. Okay, so coming back to the presentation, I will now focus on the origin of radio relics because this is my focus. So as I said from the beginning, it was clear that radio relics are connected to the presence of shocks, and we know that in shocks there are Fermi-1 processes that can accelerate particles. And the first idea was that particles are accelerated by the so-called diffuse shock acceleration process, that scattering back and forth electron on the edge of the shocks. It's able to accelerate directly particles from the thermal pool up to relativistic energies. And this can easily explain, for example, many characteristics of radio relics, and in particular, the spectral index gradient. In fact, this is the radio spectrum of emission, and we know that when particles are accelerated by a shock, they gain a power law that is around with a spectral index of around -0.6, and then when the particle age, so they lose energy via synchrotron and inverse Compton losses, the spectral index become steeper and steeper. And this is what we observe in relics, where we see a flatter spectral index at the edge, so in the edge on the other side of the cluster center, while we see a spectral steepening going toward the cluster center. And this is expected, in fact, if a shock is accelerating these particles. But in this theory, there is a great problem. That is the efficiency of the particle acceleration process. In fact, the shocks lose energy via thermalization and acceleration of particles. But while the thermalization efficiency is quite high, also for low Mach number shock, the acceleration efficiency drops for low Mach number. And as I said, we observed that shock wave in the external part of clusters have low Mach number between 3 and 5, but also lower. So while this process is able to explain, for example, the emission from supernova remnants, where the Mach number are higher, it's more difficult to explain acceleration directly from the thermal pool for low Mach number shock waves. But still, relics exist. So the question is, which are the other ingredients that we are missing? First of all, the DSA from the thermal pool is not totally excluded from all the relics, but it's valid for some relics. For example, this is an example where we found high Mach number, so for example, higher than 3.5, or low radio power. like, for example, this. So, of course, the DSA is the main ingredient of acceleration in radio relics. But as I said, more ingredients are needed. For example, there is a possibility that the electrons that are accelerated by shocks are not the one from the thermal pool, but some electron that was previously accelerated, so that constitute a fossil electron population that can be then reaccelerated by the shock. And here the question is, which is the origin of such fossil population? Can be of AGN origin, and this was observed in some relics. This is a sketch, for example, where an AGN inject particles into the cluster, into the intercluster medium, and then particles are reaccelerated by the shock passage. Or it's another way is that there is not just a single shock traveling in the ICM, but multiple shocks can progressively reaccelerate particles. This is what we also saw in the previous simulation. And in this way, the energy gained by the final shock is it's higher than from the thermal pool. Or there are other ways to pre-accelerate particles. For example, this is just an example. This is called shock drift acceleration, and this is a mechanism in which particles can be pre-accelerated at the shock, and this depends on the upstream magnetic field. This is just studied in simulation, and it is very difficult to prove in observation because we don't have information on the upstream magnetic field in galaxy cluster. But it's a possibility. And other possibility, for example, is that there is an amplification of the magnetic fields in the region of relics, so that, of course, the total radio power of the relics can increase. So in general, there is, of course, a tight connection between the efficiency problem, so the origin of radio relics themselves, and cluster magnetic fields, of course. So what we know from cluster magnetic fields is that they have a radial decrease, so they have a strength of order of few microgauss at the center of cluster, and then they decrease going into the outskirts, following basically the thermal electron density distribution. And we know that they are very complex, meaning that they fluctuate, they are turbulent on a lot of scales. But there are still a lot of open questions on the magnetic fields in cluster. In particular, we don't know exactly which is the structure of magnetic field in cluster, meaning which are the scales on which magnetic field can fluctuate in cluster. And we don't know if these depend on the mass or the dynamical state of galaxy cluster. Then we expect that in relics, the magnetic field can be modified by the shock passage, but we don't know if and how much the magnetic field is amplified, which is the structure of the magnetic field in the shock region, and if this is consistent with acceleration models that I showed you before. This is another simulation where we see a zoom in a galaxy cluster, and we see clearly that magnetic fields are turbulent in clusters, and we know this, of course, from simulation, but we have also probed with observations. But we also see that in relics, we have a high fractional polarization, as I said at the beginning. So they reach also 60% of fractional polarization. And the magnetic field is very aligned on megaparsec scales. Here in this example, we see the electron vectors in red, and the magnetic fields that is, of course, perpendicular, that is well aligned along all the on the sides of radio relics. So what happens in radio relics? The idea is that the turbulent medium, the turbulent plasma, where the magnetic field is attached, of course, to the thermal electron density, is compressed by the passage of the shock. So it is at the beginning, it is isotropic, but when the shock passes, it can amplify, but not strongly, the magnetic field, and stretch it along the direction of the direction of the shock. So that means, and then the magnetic field is again turbulent after the shock passage. This is called turbulent compression, and this was probed with this simulation, so a simulation plasma MHD simulation in a box. So where they found that, in fact, the shock passage can order the magnetic field line at the edge, and amplify them by a factor of about 2, so no strong amplification. But of course, this needs observational evidences. So before going to some of our results, I will briefly go through the let's say the theory of what we can understand from polarization, using polarization, and what are the methods that we can use. So basically, if we have a polarized source, this means that the polarization vector have two intrinsic quantities, so the P0, so the length of the vector, and its angle, so the polarization angle. And of course, the polarization vector is perpendicular to the magnetic fields at the source itself. When the polarized, linearly polarized emission pass through a magnetoionized medium, so a medium where magnetic fields and thermal electrons are present, this generates a rotation of the polarization vector, so that then when we observe the polarization of the source, we obtain it a smaller polarization and a different polarization angle. And this is due to two effects that is caused by the so-called rotation measure. So what we obtain at the end is a different polarization angle that is rotated by a certain amount that depends on the rotation measure and on the lambda square of our observation. And the rotation measure is defined as the path integral of the thermal electron density and the magnetic field along the line of sight. And the dispersion of the rotation measure along the line of sight give also an exponential decrease of the intrinsic polarization of the source. So basically, we have a lot of information from this. If we are able to recover the P0, so the intrinsic polarization and the polarization angle, we have direct information on the level of homogeneity of the magnetic field at the source and the magnetic field direction, referential magnetic field direction at the source, because we know that the fractional polarization only depends from the index, the power law index of the electron distribution at the source itself. If we have also information on the rotation measure, we can have some information on the other component of the magnetic field. So the magnetic fields where the linearly polarized sources has passed through. But we can know information on the magnetic field only if we are able to invert this integral. So if we have information on the thermal electron density and the magnetic field. So normally we do this in comparison with the 3D simulation. We can also measure the decrease in the polarization, and this can be due to different effects. For example, we can have internal depolarization. For example, if the source is not in the background of the rotating medium, but is inside it. So, for example, we have different layers of emission within the medium, like, for example, in cluster. When we observe our source in our resolution beam, we can have the mixing of polarization angle in our resolution element. And this causes depolarization because, of course, the different vector, when they sum, of course, they lose the information of their direction. And so they mix together and decrease the total polarization. So when we observe internal depolarization, that means that we have filaments or different layer of emission inside the source, and also turbulence within our source. But we can also have external depolarization. For example, if we observe a source and different level of polarization from two different positions of the source, we can expect projection effect because one part of the source is farther away, so it's more rotated by the Faraday rotation effect, so that we obtain lower polarization with respect to the nearer part. But we can also use the depolarization to study the scale of turbulence. For example, if we observe the same source, but with different resolution element, we will have a higher depolarization at lower resolution. So when we increase the resolution element, we lose polarization. And this tells us about the size of the turbulence of the magnetic fields in the medium. So we have a lot of information. Some of them is direct. So we have direct probe of the magnetic fields at the source if we can measure these quantities. And we can have some indirect estimate of the magnetic field properties of the medium. If we can have information also on the rotation measure and on the depolarization of sources. So now that we have the big picture almost clear, and we have some technical way to understand properties of magnetic fields thanks to the polarization of radio relics and other polarized sources, I want to go into some results where, in some words, where we try to answer the question that I raised in the first part, in the introduction part. So the first work that I want to talk about is a work where I collected a number of double radio relic systems. As I said in commenting the video, in some cases, we are so lucky that we can observe two relics in the same cluster. And this is an example. So we have two relics, more or less of the same size on the two sides of the cluster. And in this case, we also have a central radio halo. And in this system, what we expect from our simulation is that this system comes from binary merging system, mostly lying on the plane of the sky. So that means that in this system, we expect to have a clearer major geometry, and this is also confirmed by optical studies, and so minimal projection effect. So we expect to see edge-on relics, so that their properties should be more easily compared. And also we have a higher detection chance because, as I said, they are seen edge-on, and so we have a higher chance of detection both in total intensity but also in polarization. So we have a total of 22 double radio relic galaxy cluster out of 60 radio relics known, more or less, because there are always new relics discovered now. But as you can see, they are the majority because we have 44 relics out of 60 known that lie in double radio relic systems. And 15 out of 22 have polarization information in literature, and 9 of them have Faraday rotation information. And in this work, we added 4 to this list with the polarization and rotation measure analysis. And if, for example, in this plot, you see in yellow the total intensity emission, so the total radio emission of the system, and in white reddish color, you see the polarized emission of this relic, while this relic is not observed in polarization. So from this work, I made a compilation of polarization and rotation mode properties of relic at 1.4 gigahertz. And I searched, I searched for a correlation between polarization and rotation measure properties and physical quantities. As I said, from the expectation of the turbulent compression scenario, so the one that I explained you before, we expect a correlation between the fractional polarization of radio relics and the Mach number. This is because, of course, the Mach number is aligning the magnetic field line, and so the stronger is the shock, the stronger is the alignment, and the stronger is the fractional polarization. So this is some trend that we expect, so increasing fractional polarization versus the Mach number. And I reproduced this plot with our data, but now we have the polarization at 1.4 gigahertz, that is the one that we can observe, versus the Mach number derived from our radio analysis. And this is the trend that is not very, straight trend. Each point here is a relic, and the blue point are the average fractional polarization, while the orange one are the maximum fractional polarization for each relic. And we found a weak positive correlation between these two quantities. So this is in line what we expect. I mean, the positive correlation is in line from what we expect from compression scenario. But we interpret the fact that this correlation is weak with the fact that there are depolarization effects. So that what we observe at 1.4 gigahertz is not the intrinsic polarization, but was already depolarized by some effect. So we wanted to study which was the source of this depolarization. So it could be due to external beam depolarization, so to the fact that different polarization vectors are mixed within our resolution element, or to internal depolarization, so to the presence of turbulence and filaments inside the relics themselves. To prove that, we here I plotted the fractional polarization against this time the beam size, so the resolution element in kiloparsec of our observation. And again, you see there is not a correlation in this plot. We didn't find a correlation. And I also color coded each point with the projected distance from the X-ray peak, so the distance of the relic from the cluster center. That is also can give us an indication of projection effect that can also influence the depolarization. So this is telling us that the beam depolarization, so the depolarization that is external and that is connected to the resolution element, is not the main driver of depolarization. And this is again well motivated in the context of turbulent compression. This is from another work where we have from simulation, the mean polarization fraction of relics against the beam physical scale. Again, you can compare these two plots. And you can see that all the observations that we have a resolution lower than 10 kiloparsec. So more or less, they are all here, so in this region, where we don't have a great trend with the increase of the physical scale of our resolution element, but the difference between different fractional polarization is given mainly by difference in the turbulence scale. And these are the two colors, blue and violet, and also on the presence or not of internal depolarization. So this is the difference between solid line and dashed line. So we have a large scatter in this area due to different turbulence, both inside and inside the relic itself. So this is again a confirmation of the presence of internal depolarization. Finally, I write here the global Faraday rotation properties. So the fact that the average rotation measure of all these sources, excluding one that has a higher rotation measure, is lower than 40 rad per square meter, while the dispersion of the rotation measure in front of the source, so external, is lower than 30 rad per square meter. And these values are consistent with the fact that we are observing sources in the external part of the cluster, seeing a zone, and these values are due to the external ICM, intercluster medium, with an average magnetic field of 1 microgauss. So these properties are consistent with the picture that we have of double radiorelic system. But if we compute the fractional polarization that we observe at 1.4 gigahertz, using a reference value for P0, that is what we expect from compression, and the obtained value for the rotation measure dispersion, we find higher value than what is observed. This means that we have more depolarization than what is expected from just external depolarization. And that this again confirms that we need to have internal depolarization due to complex or filamentary magnetic field structures within the relics themselves. So this concludes, let's say, the first study that I want to tell about today. And our conclusion is that polarization and rotation measure properties of a statistical sample of double radiorelics confirm the turbulent compression scenario. That means that magnetic fields and thermal electron density are turbulent in the downstream of relics. So that means that the shock can align, magnetic field line at the shock edge, but then the medium becomes again complex and turbulent in the downstream. And both internal and external depolarization are present at 1.4 gigahertz, and this has to be taken into account into statistical studies. and also in the computation of acceleration efficiency in the downstream of relics, because in the downstream we can still have turbulent reacceleration of particles, and or presence of several shock surfaces that can constitute the filaments that we kind of see in polarization. So that means that an additional reacceleration can be present after the shock passage, basically. Now I will move on into the study of one of these double radio relic system. I call this a lucky cluster, and I will explain why. This is Abel 2345. And here we see a X-ray image of this cluster on the background from XMM Newton, and on the top we see radio contours, high and low resolution. And in this cluster we have, as I said, two relics, one on the east and one on the west. The one on the east is a more classical radio relic, I would say, with an arc-like shape, while the one on the west is a bit anomalous, let's say, probably because this is not clearly a double, a binary merger, probably, but there is also an interaction with a subgroup that we can see here in the X-ray, like a bullet passing in this direction, and this is probably changing the morphology of this second relic. And here you see a zoom in of both of these two systems. You can see that clearly also this relic that seems to be quite arc-like shape in reality has a lot of substructures at high resolution. I call this a lucky cluster because we detect, of course, the two relics in polarization, but we also detected 5 sources that show polarization within the relic. And this is not obvious because most of the sources in cluster are depolarized due to the turbulence in the intercluster medium. So it's difficult to find so many sources in the cluster or in the background of it that are also polarized. And in this case, here you see a zoom in of the central region of the cluster. This is the brightest cluster galaxy that is not polarized, but we have two tail radio galaxies that are probably spinning around the central potential point of the cluster. And these both are polarized, and also these other cluster galaxy that has a long tail. And then there are galaxies 3 and 4 that are probably background galaxies, so not embedded in the cluster, but seen in the background. And here on the right, you see the polarization fraction of the two relics. And these are the color scale. You see that they reach also high fractional polarization, mainly in this part of the eastern relic and in this part of the western one. And this confirms also the fact that there is probably a component of the merger of the shock that is created by the presence of this subgroup, because we see higher polarization in this direction that is not generally expected from shock traveling in the other direction. And the gray line are the magnetic field line. So you see that here they are well aligned with the main length of the eastern radio relic, and here also they mostly follow the main elongation of the western relic. So from these sources, from all the polarized sources, we derive the rotation measure using the technique called rotation measure synthesis. And we also derive the median absolute deviation, that basically is a measure of the rotation measure dispersion in front of each source. And this is not affected by the galactic foreground, that is also a component in the rotation measure, so that this gives us a good estimate of the rotation measure due to the ICM. In fact, here we plotted the MAD of the rotation measure versus the X-ray surface brightness of each source, at the position of each source. And they are, you can see they are from 0 to 4, and here I plotted also the two relics. And there is clearly a decreasing trend of the rotation measure dispersion versus the X-ray surface brightness. And this is expected, in fact, if this is due to external ICM, meaning that at the center we have a higher turbulence, higher path through the medium, and so we have a higher dispersion in the rotation measure with respect to the outskirts. But this is, of course, a combined effect of the thermal electron density and the magnetic field that is rotating the polarization angle of these sources. So in order to disentangle the two effects, we have to compare this measurement, this plot, basically, with some constraint on the magnetic field and the thermal electron density in our cluster. And to do this, we made a comparison with an semi-analytical simulation using the Miro code that was introduced in this paper. And what we did is, first of all, to produce a three-dimensional thermal electron density distribution based on X-ray observation. So we use our X-ray observation to make a spherical model, basically, of our system. Then we construct a 3D magnetic field distribution, and this has to have two ingredients. One is the power spectrum that we derive from MHD cosmological simulation from this work. This is basically the power spectrum. So the power at different scales of fluctuation of our magnetic field within the cluster. So this is the analytical formula. And the other ingredient is the radial scaling with the thermal electron density. So this is the profile. So it has an average central magnetic field and a decrease with the thermal electron density that goes with the with this eta power law index. This was taken from observational result, but is also motivated by theory. And this is the case that was found for the coma cluster, that is one of the best studied systems in this field. So now that we have a model from the thermal electron density distribution and a model for the three-dimensional magnetic field, we can build a mock rotation measure map of the galaxy cluster and extract the rotation measure dispersion for each of the observed sources in order to reproduce the profile that we observed. So this is what we did. So in the point are the same profile that I showed you before. The line are the simulated profile that we reproduced with our observation. We tested the different values of eta and p mean, that means different value of the central magnetic field. And we found that this was the best profile that is able to reproduce our system, excluding the Western radial helix. But as I said, this was a bit, it's clearly in a non-symmetrical part of this system. So we excluded this from the analysis. Then we repeated the same analysis, but only in the eastern relic sector. So now including only the 0, 4, and eastern relic source. And we derived again the best profile that was able to describe our data. And we found that this is consistent with the previous, the profile that was previously described in all the system. So from this, we concluded that no magnetic field amplification was needed in the region of the relic to explain the profile that we observed in this sector. And we also derived the magnetic field at the relic that is of about 0.3 microgauss. So for this system, we concluded that there are no evidences of magnetic field amplification, and we were able to derive the magnetic field profile from the center up to the region of the relics with this semi-analytical simulation. Then we compare our results with other similar studies performed on other galaxy clusters. And these are the different eta and B0 value that were found in other systems. These are color-coded by the mass of the system, and square and circle represent relaxed and merging galaxy cluster. This is a coma cluster that, as I said, is one of the most famous studied systems, and this is Abel 2345. As you see, we have very few systems where this kind of study were performed. This is mostly due, as I said, for the lack of polarized sources that we can use to perform this kind of study. But from what we have up to now, there is not a clear mass dependence of the magnetic fields in this system, and also no merging state dependence. So it seems that more or less the magnetic field profile in cluster is similar for different galaxy clusters. So this is the second result that I want to draw to your attention. So in this system, we found no evidences of strong magnetic field amplification by weak shocks. This is again consistent with just the turbulent compression that I showed you before. And with these 5 polarized sources, we were able to constrain the magnetic field in Abel 2345. And we found no mass or dynamical state correlation with the magnetic field properties. But as I said, the number of studies are still low. So this leads me to my more general conclusion. So as I think I will show you this, that diffuse radio emission in galaxy cluster is a key evidence for the study of cluster magnetic fields. And this is very fundamental for many studies, not only for the physics of galaxy clusters, but also for cosmic ray acceleration mechanism and to magnetic field origin itself. The polarization properties of radio relics allow us an in-depth study of their origin, but also into the fundamental process that happens in the ICM and that can lead to particle acceleration and magnetic field structure and strength amplification. So as I said, the number of studies, both on radio relics, but mainly on the magnetic field of galaxy cluster, are still low. And this is mainly due to observational constraint, meaning that we don't have many sources that are observed in polarization up to now. But new radio telescope, like for example MIRCAP in South Africa and ASCAP, the SKA Pathfinder, Australian SKA Pathfinder, are really driving the interest of the radio astronomical community into the use of polarization in order to understand radio relics and diffuse cluster radio emission, but more, I would say, into the cosmic magnetism origin. And this is one of the key science projects of the SKA, that is the main radio astronomical facility that will be probably ready by the end of 2030. And so I would say that the future is bright for radio polarization and magnetic field study in general. So I hope I convince you that this is really an interesting subject. And thank you for your attention, and I will keep questioning.
Thank you very much, Chiara. Very interesting talk, I guess, especially for our polarization experts here in the Institute. So does anyone have a question for Chiara? Andreas? Please go ahead.
Thank you for this very interesting talk. I was wondering about the turbulent magnetic field amplification. Would you expect to see the same effect when you have radio lobes, where you have like an AGN depositing electrons forming a radio lobe? At the front of the lobe, you have a compression of the intercluster medium. So you would expect to have magnetic field amplification in that region. And would that be comparable?
I would say yes. I must admit that I don't know about the Mach number. I don't know about the strength of the shock that is traveling also in the jet, in the lobes of radio lobes. But surely, I think I heard that there are some recent work where we start really to see also some shock component also in the X-ray emission nearby lobes. So of course we have some cavities in the X-ray that tell us about the interaction between the lobes and the X-ray, of course. But we, in some cases, we also see some compression, so due to some shocks. And in some cases, we also observe polarization. So meaning that in that region, the magnetic field is aligned by the shock and it's also compressed. So we expect some level of magnetic field amplification. Yeah.
Okay, thank you.
Anyone else? Carolina, I think.
Yes, can you hear me?
Yes.
Okay, thanks, Chiara. Very nice talk. I'm not really an expert on galaxy cluster and relics. If I understood correctly, so in the cluster where you suggest that the two relics are the polarization and the radio emission there is more associated with turbulence than not particle acceleration in shock, right?
Well, particle acceleration in shock is surely present. The depolarization is mostly caused by turbulence, and therefore that means that in the downstream of shock there is still turbulence, and this is able to partially reaccelerate particles also in the downstream. So that the acceleration and the emission is mainly driven by the shock, so the acceleration by shock, but there could be a subcomponent of reacceleration also in the downstream driven by turbulence.
Ah, okay. Now it's more clear.
Yeah,
Thanks.
Sorry.
Thanks.
Yeah, also because I didn't mention it, but another problem that we have for most of the relics, it was computed that we expect them to be.
I think we have problems.
It's not me, right? Okay.
No, I think it's Chiara's.
Energy, but they can in some way be reaccelerated by the turbulence itself.
Sorry, Chiara, can you hear us?
Yes.
Okay, because you got frozen for
Sorry. Yes, I had. Sorry, but I was just adding, but the answer that I give you was that one. So I don't know what you lost, but yeah, it was just an update.
If you can
okay.
repeat most of it, we lost most of it.
Okay. No, I was just saying that the another problem in order to explain the origin of relic is their width, meaning that for most of them it was measured that we expect them to be much thinner than what is observed. And this is another hint that it's possible that the particles in the downstream of the shock doesn't simply cool down, so lose energy via synchrotron and inverse quantum losses, but can be reaccelerated by the turbulence. So that could be an interplay between shocks and turbulence.
Mm-hmm. Okay. And in this line still, do you have, because you show us this very nice also comparison between observation and simulation, do you have any map of the EVPA's orientation in this, since you measure also rotation measure and so on? Do you have any image or map?
You mean from the simulation?
No, from the observation themselves, to see how order is.
Sorry, maybe it's AVPA. What do you mean for AVPA?
The electric vector position angle.
Okay. Sorry, just another name.
The polarization
So
vector.
you mean the polarization angle, meaning?
Yes.
Yeah. Okay. I don't have a map here. But yeah, I think that here I just have for these two relics. So this is the magnetic field vector. So
yes.
Of course the polarization vector is perpendicular to it. Yeah.
Yes. So okay. Yeah, that's quite following what you expect in a shock, right? So you
exactly. Yeah.
I was just wondering if you have something more. I don't know if you see something more a more turbulent magnetic field also.
Yeah, this is a good question. Basically, the thing is that we need to go to higher resolution, because the idea here is that when we smooth the resolution, we only see really the more ordered part of the emission. So when the magnetic field is aligned with the shock. And if we manage to go more at high resolution, we will start to see more complex behavior. And if this is some kind of self, for example, there is a work from the Gasperin et al. 2023, I think, or 22, where there is a famous double radio relic system in the south that was observed with MIRCAT at very high resolution. And there you really start to see complex behavior of the polarization angle, and also of the electric field vector. So that's kind of follow the filamentary structure of the relics, and also I mean are really more complex than just aligned with the shock front.
I see. Interesting. Thanks.
You're welcome.
Okay. Anyone else with questions for Chiara? If not, I have one very high level question regarding your one of the last figures where you were trying to show correlations with the dynamical state
yeah.
of the cluster.
Yeah.
That one, yes. So what is your if you would have to put more points there, what are your expectations? Would you expect that that there would be any relation between
I mean, I would expect a relation with the mass of the system, and this is because when we have a high mass, that means that the merging event was highly energetic, and this means high energy driven into turbulence that can amplify the magnetic field in the cluster. So in general, we expect higher magnetic field with a higher mass. So I mean, I would expect lighter color at the top of this plot. Sorry, at the right of this plot. And about the eta parameter, I really don't know what to expect because yeah, the fact is that for the coma cluster, this eta index was found to be 0.5. That means equipartition between the thermal energy density, so the equilibrium between thermal energy density and magnetic field energy density, in this case us and to the two. So we would expect equilibrium basically in physics, but for most of the system, we found that this index is higher. That means that in the external part of the system, we see a stronger increase of the magnetic fields with respect to the thermal electron density profile. So I don't think that I would expect a trend, or I don't know which trend to expect. I don't know. With it, I don't know. It's more clear for B0, but I mean, still, I mean, I don't see any trend. So I think we need first to increase the number of points. First to verify the increase of the magnetic field with the mass and also with the merging history. So what we expect is that for a system that just undergone the merger, we expect a higher amplification of the magnetic fields with respect to relaxed system. So.
Mm-hmm. Okay. Thanks. Last call for questions. Okay. If not, well, thank you again, Chiara, for the talk.
Thank you.
Really interesting. And yeah, I think we can stop it here and wrap it up.
Okay.